Hello everyone, I welcome you all in this lecture. So in this lecture we will cover the aircraft longitudinal dynamic stability. So we have already covered the static stability part and I have explained to you what do you mean by the aircraft static stability. Fundamentally, when it has a initial tendency to return back to the original position when it is being disturbed from the equilibrium position, this is known as a static stability, and we have found out the associated coefficients and derivative. For example, Cm alpha, if it is negative, it is statically stable. And also considering the complete aircraft, I explained that Cg should be ahead of the aerodynamic center in or neutral point in order to make the system statically stable in a longitudinal case. Okay, so here we will cover the dynamic stability part. So dynamic stability, that means how the aircraft will behave over a time. For example, if if the aircraft is being disturbed from the equilibrium position and the oscillation is first increases and then with the time it is getting damp out, you can see in the case A. Okay, and then it is called positive dynamic stability. And if the oscillation is getting increased over a time, then it referred to as a negative dynamic stability. That means basically it is an unstable system dynamically. And when the oscillation is not increasing or decreasing like the case C, then you may say this is a neutral stability case, right? In this lecture we also cover the mathematically how the dynamic stability, I mean to say, look like, and who will provide the dynamic stability to the aircraft. For example, in this figure you can consider there is a two cases where you can see one ball in this curve. If you disturb, it will return back to the original position. Initial tendency, static stability, but over a time, dynamic stability. Another case, when you place a top ball over this surface, then if you disturb, it will never come back to the original position. So statically unstable also and dynamically unstable also. Okay. Now very fundamental questions, and one thing I want to clear this: it is not all every time it is like a oscillation only. The simple convergence and divergence can also be there instead of oscillations. Okay. So if it is converging over a time, it is dynamically stable. If it is diverging over a time, it is dynamically unstable, and it is remains the constant. It is neutrally dynamically stable. Okay. So but the very fundamental question is this: if the system is statically stable, can the same system be dynamically unstable? It's a very fundamental question. So since this we are talking about the aircraft, considering the aircraft, we are explaining all the concepts. So I will take the aircraft here and I will try to explain this. Let's say aircraft is disturbed from the equilibrium position in Ya. So it has a restoring tendency to get back to the original position. And since Ya and roll is coupled, okay, so in this case, the aircraft may roll also. So that means even though the aircraft is directionally stable, okay, but due to coupling with the roll, it may lead to the oscillation and the motion can diverge over a time. So this way you can say it is statically stable but dynamically unstable. So in a reverse way you can say if the system is dynamically stable, it should statically be stable also. Okay. All right. And the curve which I have shown, the converging over a time, diverging over a time, the solution is written x equal to x naught e to the power lambda t. So lambda is nothing but the root. If lambda is negative, it is statically the stable system, I mean to say. and if it's a lambda is positive, that means it is unstable case. So okay, in next lecture I will try to take physical aircraft example, and we'll try to linearize the system, and we'll try to decouple, and we'll try to find out the aircraft mode and the route we will plot on the route locus, and you will have a physical feel, I mean to say real feel, how, what do you mean by the dynamically stable in longitudinal case. Okay, okay, all right. Okay, so as you know, when you take a pendulum, if you disturb from the equilibrium position, over a time it will come back to the original position. So the question is, who is providing the damping? The simple answer is air. So in this case also air will provide, but air will automatically will not provide the damping. You have to design the aircraft, you have to design the component, and you have to design in such a manner you can get the support from the air. So wing dihedral, swept back, vertical tail, horizontal tail, all will provide the damping. Okay, here we are focusing about the longitudinal dynamic stability, so we will consider the horizontal tail, which provides the main contribution towards the damping. Okay, and always these things you can relate to the uh, fundamental, and you can say very primary system, like a spring mass system. Mx double dot plus Cx dot plus K is equal to external force, and here C is a damping coefficient and K is the stiffness. So if you relate this K, you can relate with the same alpha in aircraft case, and C with the derivative which will be obtained in this lecture. Okay, so now we will find out the lift and moment due to tail, and this will provide the damping. Okay, force term and moment term. So the change in tail lift, for example, if the aircraft is pitching, okay, so you can write half rho v square, half rho vt square st cl alpha t into delta t. Okay, so here rho is the density, vt is the velocity at the tail, so v is the velocity at the wing, and vt is the velocity at the tail, because you will see some poor airflow on a tail or not the exactly flow over a tail. So that is why we have deficient with v and vt. St is the tail area, cl alpha t is the lift curve slope of a tail, and delta alpha t the change in angle of attack due to pitching. Okay, so now consider the aircraft CG and aerodynamic center. In between the distance is LT, that is called tail arm. So if the aircraft is pitching, so basically you can consider this is a radius LT, and with the pitch rate Q, so from V equal to R omega, you can write the change in angle of attack QLT by V. V the velocity with the aircraft is flying. Okay, and now you can find out the delta Z. So delta Z, that means we are recording the coordinate system, the Z is pointing downward and lift is acting upward, so that is why delta Z equal to minus delta T. Okay, so the coefficient you can find out Z divided by half rho v square S. Dimensionalize these things, very simple. Take a delta and finally you will read minus eta st by S CL alpha of the tail QLT by V. So here eta is nothing but the ratio of dynamic pressure at the tail and wing. Okay, so if the same airflow is received by the tail, eta is 1. Okay, dynamic pressure is received by the same. Okay, so CZQ you can find out dou Z by dou QC by 2V. So here QC by 2V is a non-dimensional factor, because okay, if you divide by Q, it has some unit. So C by 2V if you do, you will non-dimensional. Okay, this is standard. Okay, take 2V by C bar outside, so you will get dou Z by dou Q. Put this value, you will get CZQ equal to minus 2 eta Vs CL alpha of the tail. Now the new term is coming Vs. So Vs you can write ST LT by SC bar. So that is nothing but the tail volume ratio. It also tell you the how much aircraft is stable. If it is close to 1.9 or 1.1, it is more stable, and if it is 0.2, 0.3, 0.4, it is I mean to say less stable. Okay, so this number also tell you the how much aircraft is stable. For example, in commercial you will find the close to 1. and in the fighter you will find 0.1, 0.2, 0.3 like that. Okay, now this is all about the force part. What about the moment? So moment you can write about the about the center of gravity. So change in moment you can write change in left into tail arm, and since it is the pitch down motion is happening, you consider that you can take a sign negative. So minus delta del lt into lt will be the moment, and first finally you can find out delta z. Okay, as we have found out, which is nothing but the minus delta t. Okay, and then delta cm you can find out as you have found out delta z, and finally you can find out cmq as you found out z czq. So cmq will be minus 2 eta vs cl alpha of the tail lt by c bar. So you can see, if you place the tail far from the center of gravity, like lt is more, you will have a more value of cmq. So actually when you design any kind of aircraft, you can actually have a feel for cmq. Like cmq is large, so it will support the damping, so it will quickly damp the aircraft. Okay, and if it is close to the cg, so aircraft will take more time to damp out. Okay, so like that actually you can have a dependency, which parameter depends whether it is increasing or decreasing. So accordingly you can design. For example, if you are getting less damping, what you can do, you can increase tail arm. Okay, or you can increase cl alpha of the tail. Okay, and you can increase vh is also the part of lt. So lt is t by c bar. So already I talked about the lt increasing or decreasing. So here in vh you can actually increase the tail area. Okay, so like that you can actually play with the numbers and all, and have a feel for that. Okay, so when you in the next lecture I will show you that key what is the typical value of cmq. You will find out the minus 20, minus 10. Okay, so if you design different kind of aircraft, you will find a different value of cmq, and accordingly you can have a feel. In the next lecture we will take a physical aircraft. We will try to write a equations of motion, aircraft dynamics. So already I have explained in the flight control system design course aircraft dynamics. You may go and check. So in the next lecture we will take one example, glider aircraft. Okay, powered glider aircraft. It is also called motor glider, and we will try to see different aircraft mode. In a longitudinal case we will find out short period mode and Foucault mode, because in a reality systems are coupled. Okay, but when you decouple, you can actually check the behavior of aircraft using the aircraft mode analysis. So we'll found one mode we call short period mode, and another mode will call Foucault mode. So in reality, in some trim condition the short period mode is dominant, and in some trim condition longitudinal mode is dominant. But when you decouple, you will see exact picture. Okay, so when you fly at a very low angle of attack, and then the short period mode will be activated, and when you fly a very high angle of attack, then the aircraft will be poorly damped, and then you will see the foreground mode will be dominant. Okay, so we'll meet in the next lecture. Thank you so much.